So in this video, we're going to be looking at satellites and their applications. So these are the learning intentions that we're going to cover in this video. So number one, many satellites orbit the Earth in circular orbits. You need to explain why the center of the circular orbits must coincide with the center of the Earth, and you need to be able to do a derivation and explain that the speed of the satellite is only dependent on the radius and the mass of the central body, not on the mass of the satellite. So, number one, explain why the centers of the circular orbits of Earth satellites must coincide with the center of the Earth. Well, we know between two bodies of mass, there's a gravitational force between them. So if this is the mass of the Earth and this is some satellite, we know that the gravitational force acts between them and between the centers of these two bodies. Now, in order for uniform circular motion to occur, so this satellite to be whizzing around the Earth at constant speed, so in order for that uniform circular motion, we know that there is a centripetal force acting towards the center of its circular motion. So that centripetal force is causing centripetal acceleration, and that must be directed towards the center of the satellite's path. So therefore, in order for the gravitational force, it's going to be between the center of the bodies, and in order for uniform circular motion, that force has to be directed towards the center of the circular path. So therefore, the center of the orbit must coincide with the center of the Earth in order for uniform circular motion of a satellite to occur. So like this, orbit around the center of the Earth. As you see later, we can actually have orbits around the equator, and we can actually have orbits around the poles, but it's still coinciding with the centers. The centers need to coincide. So we can't have an orbit around just the North Pole like this. The force between the bodies, this is not going to be causing uniform circular motion. The force is just acting in the wrong direction. So that's not possible. So you need to be able to do a derivation. So you need to be able to derive this. Now this is on your formula sheet, but you need to be able to derive this one. So this is the speed of a satellite moving in a circular orbit with a radius of r. Now, when an object is orbiting around a planet, the planet's gravitational force is acting towards the center of the satellite's path, and that gravitational force is acting as a centripetal force. So what we can do is we can set the centripetal force equal to the gravitational force. Now, remember, there isn't a formula for centripetal force, but there is F equals ma, and there is F equals ma, and there is acceleration is equal to speed squared over r, and we can replace a with v squared over r, so the centripetal force is this one here, mv squared over r. And we know that the force due to gravity is the universal constant, and then the mass of the two bodies divided by the distance between them squared, which in this case is the radius of the orbit. And if we look at these two sides of the equation, once we've set the centripetal force and the gravitational force equal to one another, you'll notice that the little mass of the satellite on both sides can cancel out. And then what we can do is we also have divide by r on each side, so this r will cancel with one of the r's here. And we're left with the speed squared is equal to the universal constant times by the mass of the central body divided by the radius between them. And then we can square root both sides of the equation to derive speed is equal to the square root of the universal constant times by the mass of the central body divided by the radius squared. Sorry, not squared, just the radius. Now, note, this equation here does not contain the mass of the object or the satellite. That mass was cancelled out. So that mass, the mass of this satellite here, has no effect on its speed, and the speed is only dependent on the mass of the central body and the radius of the orbit. Now we're going to look at some applications. So you need to be able to explain why a satellite in a geostationary orbit must have an orbit in Earth's equatorial plane, and I'll explain what that means in a second. And it's going to have a relatively large radius, and the satellite must orbit in the same direction as Earth's rotation in order for it to be stationary. And you need to be able to explain the differences between polar, geostationary, and equatorial orbits. and you need to know the different applications of these different satellites. So, obviously different satellites are used for different purposes. Now, an equatorial orbit is simply just an orbit that moves directly around the equator. So this one over here is moving directly around the equator. That's an equatorial orbit. Now, a geostationary orbit or satellite is a satellite that remains fixed in the exact same point. So this satellite remains fixed at this point. Now, the only way it can remain fixed here is if its speed matches the speed of the rotation of the Earth. So a geostationary satellite must orbit from east to west, so in this direction, from east to west, because that's the way the Earth spins. So the satellite is actually moving at quite a fast speed. However, because it's matching, so scientists can calculate, and later on when we look at Kepler's laws, we can work out the period, and hence the speed it needs to travel at in order to match the speed of the Earth's orbit. And we know that the period of an Earth day is 24 hours, so we can actually match the orbit of the satellite to 24 hours, and therefore the satellite stays in a stationary position if it matches the Earth's rotation. Now, later on we'll see that in order to have a period of 24 hours, it needs to be going at a very high speed. It needs to be really high up in the Earth's atmosphere. It's almost 36 Ks. So geostationary orbits are really high in the air, and unfortunately because of... I'll talk about the applications in a second. So geostationary orbits are stuck in one spot, but they match the Earth's rotational speed, and they have to be around the equator, because otherwise the center of the satellite wouldn't match with the center of the Earth, and it wouldn't cause that uniform circular motion, which we described earlier. So the center of the satellite, so it has to be along the equator in an equatorial orbit, and it's geostationary because it matches the Earth's rotational speed. Now, advantages. It can, because it's so high up, it actually monitors a large portion of the Earth, approximately almost a third of the Earth. So it can track weather events and large-scale weather events. However, because it is so high up in the Earth's atmosphere, it doesn't take very good quality photos. And so it can't be used for surveying area or even meteorology. So it can track weather events, but it's too far away to actually be too advantageous. And also because they're so high up, there's actually issues with sending and receiving signals to Earth, and because there can be refraction of these signals in Earth's atmosphere, and there's also a bit of a time delay. So they're up high, so they can cover a large portion of the Earth, but because they're up so high, the image quality isn't great. Now, the other type of orbit is a polar orbit, or a polar orbit satellite, and these orbit around the north and south poles. You can see this blue arrow here. Now, they're much closer to the Earth's surface, and because they're much closer to the Earth's surface, so they don't need to match the Earth's period, right? So they're able to travel at faster speeds, and so they can actually approximately complete 14 orbits around the poles per day. So advantages, they can cover more of the globe around the north and south poles, so it can view different parts of the Earth with each rotation. So if you see this diagram here, as it's rotating around, it's going to get different parts of the Earth as the Earth rotates around. But there's going to be snippets where it doesn't cover anything and it misses that area. So it's not continuous viewing, that's a disadvantage. But because it is much closer to Earth's atmosphere, they take much better high resolution images. And again, so they cover more global coverage because they're going around the poles, and as the Earth rotates, they can see more of the globe. And they can take better images, but disadvantages is because they're in the Earth's atmosphere, the atmosphere can actually cause drag on the satellites and reduce their speed and hence the period. And they don't have continuous viewing, so they're not very good for, if you want to observe the same area over time, because they're constantly whizzing around the poles.